Today we're going to start talking about circles and angles. Actually, we're going to keep talking about circles and angles. Anything that you saw from my videos from before spring break, most of what we see today is actually going to be a review of that. It's still good for you to pay attention because it's been over a week and you've been on your own. The third example today, 10-27, is new material, so you really want to make sure you hone in on that. Okay. The first question we're going to talk about today is 10-25, and 10-25 says, well, what if it's a semicircle? So the word semicircle, just a vocabulary word, it means half of the circle. So in number 25, part A, it says if arc QR, so here's arc QR, is equal to 180 degrees, for this arc out here, it's an intercepted arc, then what's the measure of angle P? So this is very much a review. Okay, remember, if the vertex of the angle is on the circle, it is so hungry, it can eat twice its size. So if it can eat twice its size, then to go backwards and find the angle, then we're going to cut it in half. And we know half of 180 is 90, so angle P would have to be 90 degrees. Okay? The reason that this is really helpful is if you know that you have a diameter. So in part B, they're telling us UV is a diameter. Remember, that goes through the very center of the circle. So it does cut it in half. It means automatically, if it's a diameter, we know that's 180 degrees. Okay, so what does that mean? We know for sure that this angle T is really a right angle. It's 90 degrees. It is so hungry, it's eating twice the its own size. Okay, so to go backwards, we cut it in half. We know that's 90. So now let's keep reading part B. And part B says, well, what if we know TU is 6, TV is 8, can we find the radius of the circle? And hopefully you're looking at this and saying, oh my gosh, right triangle, Pythagorean theorem, we've done this so many times this year. So of course we do 6 squared plus 8 squared equals x squared. And when you solve that, you get 10 is x. So this hypotenuse is equal to 10. But the question says, well, what's the radius? Radius, remember, goes from the middle of the circle to the edge. So it's not 10, it's just half of that. So the radius is 5 units. Okay, so knowing it's a semicircle helps us get back to what we know about Pythagorean theorem in a right triangle. We could use SOHCAHTOA in this situation, potentially. Okay. The next question, number 10-26, we're only going to do part A. And this says, in lesson 10.1.1, we learned that a chord is a line segment that has endpoints on the circle. This is a chord. So what geometric tools do we have to help us find the length of this? Well, of course, we have to have more clues than just, hey, here's circle P, and what is this length? So the clues that we're given here is it says that the radius is 6. And again, radius goes from the center of the circle anywhere we want to around the circle. So I can put 6 anywhere I want to. But in order to help me find LM, it's going to be helpful if I connect the center to either M or L. Okay? And in lesson 10.1, we also talked about the fact that there would be a chord in here that cuts this in half. I'm sorry, it's not a chord, it's a radius. That is the perpendicular bisector of the chord. So now again, I have a right triangle. I know that this is 6. Now they give me a different kind of clue here. They tell me that the measure of arc LM is 150 degrees. Okay? Now if I know that I'm going to make a right triangle and it's going to cut the chord in half, it's also going to cut the arc in half. So if I'm just talking about this piece of the arc, it's half of the entire thing. So if the whole thing was 150, this arc, let's see, L, we'll call that N, just from N to M is 75 degrees. Okay, now what we've created is this central angle, and remember, a central angle is equal to its intercepted arc. So I have a right triangle here, and I'm going to redraw it. I have a right triangle, there's my right angle, there's the 75 degrees, and the radius is 6. So my job is really to find all of LM, but if I can find this part here and double it, I can find what LM is. So this one is not a good candidate for Pythagorean theorem. I don't know two sides, but it is a good candidate for SOHCAHTOA. So we always have to remember SOHCAHTOA, make sure we're spelling it correctly. Okay, in this case, we're dealing with a 75-degree angle. X is opposite, and 6 is across from the right angle, so it's the hypotenuse. So opposite and hypotenuse, that means I'm going to use sine. The sine of 75 degrees is equal to x over 6. Some of you like to cross multiply if you put this over 1, and that's fine. Some of you guys just like to multiply. It's been a while, so we're going to make sure that our calculator is in degree mode. I'm going to type in 6 times the sine of 75, and I am getting that x is approximately 5.795. So 795 is going to round to 80. Okay, but remember that question is asking me to find LM. So this is 5.80 here, but that means that's also 5.80. So without hitting clear on my calculator, I'm just going to hit times 2, and I'm going to find that LM is approximately 11.59 units long. Okay, so using circle information to go back and use SOHCAHTOA to help us find missing parts. Okay. The last example today is brand new. We did not talk about this at all before the break. This is 10-27. And 10-27 is showing us a circle that has two chords intersecting. E is not the center of the circle, although it would work if E was the center. Okay? And the kind of a neat trick that you can do in a circle, if you see two chords crossing, is you can create two triangles. Okay? So all I did was create two triangles. It's kind of like a bow tie that's off center. It's not symmetrical on both sides. But we do know from way back in the beginning of the year that these two angles are congruent because they're vertical angles. Okay? Then in this chapter, remember we learned that if angle B is on the edge of the circle, it can eat DA. Remember, it can eat twice its size. But look, angle C over here is also eating arc DA. If two angles are eating the exact same arc, then that means their measures are exactly the same. So what we just proved, okay, without doing a formal proof, is that triangle BED is similar to triangle CEA, and our reason is angle-angle similarity. So remember, if two triangles are similar, we can then use that idea to set up proportions to find missing sides of the triangles. Here's what I mean. At the bottom of 10-27, it's asking us if we know DE is 8, so there's 8, and AE is 4, and EB is 6, they want us to find EC. So I'm going to put an X here. So using the fact that we have similar triangles, I can just set up a proportion to solve. Okay, I can do 8 over 6, so big side over little side, equals 4 over x. Okay, 8 is between a 1 and a 0, 4 is between a 1 and a 0, so those match up. 6 is between a 1 and a 2, x is between a 1 and a 2, so those match up. When I cross multiply, I should get that x equals 3. EC is the same thing as my x, so there I have my answer.